Cathode rays. So J.J. Thomson, we're getting a little closer to modern civilization here, 1856 to 1940. So he constructed what's called a cathode ray tube, and this is similar to what's used in the old CRT televisions. CRT stands for cathode ray tube, not the flat panel TVs, but the old-fashioned ones. A glass tube that's partially evacuated. So here's this glass tube. And he passed electric current. He put a high voltage across this. And in between here, there's a partially evacuated tube. And so there's a little bit of gas in there, but not anything else. There's no wire. If you apply a high enough voltage, you can get what appears to be a beam of light going through here. And those were called cathode rays. They always go from the cathode, the negative terminal, to the positive terminal. And that's why they call them cathode rays, because they come from the cathode, they travel to the anode. So this was kind of cool. He studied these particles then. He found that the particles in this ray always travel in straight lines. They're independent of the composition of the material from which they originate. You can make tubes where the cathode is made out of different metals, but the cathode rays are exactly the same. He also found that they carry a negative electrical charge. What's electrical charge? This is a fundamental property that some particles have. Some have a positive charge, some have a negative charge. What you need to know about electrical charge is that positive and negatives, opposites, will attract each other, and like charges, two positives or two negatives will repel each other. Electrical charges behave in many ways like magnets do. We can play with magnets on the refrigerator and with Brio trains. And if you get the magnets the opposite way around, then you can't push them together, right? They want to stay apart. That's like the like charges. They're going to try to get away from each other. Turn the magnet around and it'll stick to the other magnet, right? It'll pull in. That's the attraction between opposite charges. The other thing about electrical charges is they have magnitude, and if you have a +1 charge and a -1 charge and you let them get attracted to each other and stick together, then this resulting combination here has no overall electrical charge because they cancel out. So these cathode rays were particles that have negative charges. He measured the charge to mass ratio of these particles by deflecting them with electric and magnetic fields. So here he's got his little cathode ray generator here. So he's getting cathodes and he's shooting them through an anode, and then they're coming over here, and this has a sensor on it that allows you to see where they're going. And he's got a magnet here and some partially charged electrical plates. And so he can apply an electric field and see how that moves the particles, and he can apply a magnetic field and see how that moves the particles. And what he found was that the charge to mass ratio was negative because it had a negative charge. 1.76 times 10 to the third coulombs per gram. So a gram of these had a charge of minus 1.76 times 10 to the third coulombs. Coulombs is just a unit of charge. What this implied was that the cathode ray particle was about 2,000 times lighter than hydrogen, which was the lightest known atom. And it still is the lightest known atom. And this was a very, very surprising result. Because Dalton said atoms can't be cut into smaller pieces. And here we have a piece that's smaller than an atom. That's a big deal. The indestructible atom could be chipped. You could get these little bits to come off of it. What Thomson had discovered was the electron. And we now know that the electron is part of the atom. It's a negatively charged, low-mass particle that is present in all atoms. That's why the cathode rays were the same, no matter what the cathode was made out of. The particles coming out of them were electrons. all atoms contain electrons. And this was the first evidence that elements are formed from the same particles. Different elements are formed from different atoms, but the atoms themselves do have pieces inside of them. So, I guess I should stop there for a second. Any questions about that? Like, that was strange. I don't think I understand it enough to ask a question. Is that true for some of you? That's okay. This is kind of background stuff. If you can get through chemistry without understanding these experiments. So try, but don't stress out about it. So after Thomson, an American physicist, Robert Millikan, 1868 to 1953, did an experiment with oil drops. And this experiment allowed him to figure out the charge on a single electron. Thomson had found the charge to mass ratio, but Millikan found the actual charge. So what I'm going to do now is I'm going to show you a video about this. So we watched the video, which is also on the YouTube channel. And that's helpful in understanding this. So he measured the strength of the electric field that was needed to make the drops stop falling. And from that, he calculated the charge on each drop. And he found that the drops had different charges, but they were all multiples of this number, which he decided, and correctly, that this was the fundamental charge of a single electron. After that, and getting the Thomson's mass to charge ratio, then he could find out what the mass on an electron was. Oh, I guess I was supposed to calculate that. I don't remember the numbers. It comes out to be, I think it was 1.6 times 10 to the minus 28 grams. That's a 0 and a decimal point, and 27 zeros before you get to a number, grams. That is mind-bogglingly small. Okay, just mind-blowing. And we'll save this for Thursday.